Hi, welcome to this lecture. In this lecture, we will go through what are the problems with RNN and LSTMs. So there are mainly two problems. So the first one is about sequential processing. So sentence must be processed word by words in case of RNN and LSTMs. So RNN and LSTMs can't be trained in parallel because of that. So in order to encode the second word in a sentence, I need the previously computed hidden states of the first word. Therefore, I need to compute that first, right? So it usually take a lot of time during the training if there is a huge amount of data set. So that's the one major problem. It a lot of time during the training process. So the second one is past information retained through past hidden states. So sequence to sequence models follow the Markov property. Each state is assumed to be dependent only on the previous seen state. So information in RNN and LSTMs are retained thanks to previously computed hidden states. But the point is that the encoding of a word strongly affect only the representation of the next word. So usually its influence is quickly lost after a few time steps. RNN tends to forget information from time steps that are far behind. Only for small sequences like less than 20 time steps, the performance is good. But after that, the performance started to drop. So this is the main problem they encountered during the translation of a language. So if the time steps is less than 20, the performance was good. But if the time stamps is greater than 20 time steps, the performance started to degrade. So LSTM tried to solve the dependency range, but nevertheless, the problem is inherently related to recursion. Another way is people try to solve this problem is that to use bidirectional models, so which encode the same sentence from two directions, that is forward and backward, that is from start to end and from end to start. But allowing this way, words at the end of the sentence to have stronger influence in the creation of the hidden representation. But this is just a workaround rather than a real solution for very long dependencies. So these are the main two drawbacks of RNNs and LSTM. So one is you can't uh, train them parallelly, so it used to take a lot of time during training process. And the second one is loss of information after crossing 20 time steps. So usually they are forgetting the information. So these are the two main disadvantages. So in the next lecture, we will see how transformers are trying to solve these two problems. Hi. In this lecture, we'll go through transformers, the introduction of the transformers. So we have seen the limitations of RNN in the previous lecture. So, in order to overcome the limitations of what you have seen in the previous lecture of RNNs and LSTMs, a new architecture called transformers was introduced in the paper called Attention is All You Need. I think it's around 2017. The transformer is currently the state of art model for several NLP tasks. So, the main purpose of the transformer architecture is to avoid recursion in order to allow parallel computation. So, that is mainly to reduce training time by allowing parallel computation and also to reduce drop in performances due to long dependencies. Uh, so these are the some of the properties that are listed below. So one is non-sequential. So sentences are processed as as a whole rather than word by word. So in previously we have seen that LSTMs are RNN. The sentences are processed word by word. So in this case, the transformers sentences are processed as a whole sentence rather than word by word. So another main thing is that by doing this, there is no risk to lose, forget the past information, right? That's one of the advantages of processing the sentence as a whole. So second one is self-attention. So this is newly introduced unit used to compute similarity scores between words in a sentence. So coming lectures, we will go deep into self-attention and positional encodings and stuff, embeddings and stuff. But so simple to remember that self-attention is usually helps to compute similarity scores between words in a sentences so that we can know about the relationship between different words in a sentence. So next one is positional embeddings. So another innovation introduced to replace recurrence. So the idea is to use fixed weights which encode information related to a specific position of a token in a sentence. Because in a sentence, the order of the words are important, right? Even in the language translation or maybe in other tasks, the order of the words were important. So in order to encode that information, positional embeddings comes into the picture. So in the next lectures, we will go a little bit deep into all these terminologies and how they are actually being implemented. Uh, okay, I think that's it from this lecture. We will see it in the next lecture. Hi, in this lecture, we'll go through transformer architecture at 10,000 feet view. So let's understand how the transformer works with the language translation task. So transformer consists of an encoder decoder architecture. We feed the input sentence, that is the source sentence, in this case it's English, how are you, to the encoder. The encoder learns the representation of the input sentence and sends the representation to the decoder. The decoder receives the representation learned by the encoder as an input and generates the output sentence. This is the target sentence. Let's say we are translating English to French language. Suppose we need to convert a sentence from English to French as shown in the following figure. We need to feed the English sentence as an input to the encoder. The encoder learns the representation of the given English sentence and feeds the representation to the decoder. The decoder takes the encoder's representation as an input and generates the French sentence as the output. Okay, next. If we go a little bit deep into those encoder and decoder blocks, so each encoder has 6 layers. So there are 6 encoder layers and there are 6 decoder layers. And every output of encoder is given as input to the encoder layer above it. And the last layer encoder, the output that comes from the last layer of the encoder is it's passed to each and every decoder. At last, the decoder will generate the transformed sentence. Next, in encoder, there are mainly 2 components. One is self-attention and feed-forward neural network. So in the coming lectures, we'll go a little bit deep into these layers and we'll see what's happening inside. In the decoder, the components are 3. So one is self-attention, another one is encoder decoder attention, and feed-forward layer. So the only difference between encoder layer and decoder layer is the middle layer, which is called as encoder decoder layer. So in coming lectures, we will know why this layer is needed in the decoded part. That's it from this lecture. We'll see you in the next one. Hi, in this lecture, we'll go through what is self-attention. I'll just give a basic example to know the concept. Let's read this sentence. Monkey ate the banana because it was hungry. So as a human, if you ask what does it refers here, is it banana or monkey? Usually it refers as a human, you can know that it refers to monkey, not banana, right? So how can you make the model to learn about this? That okay, it refers to monkey, not banana. So that's where self-attention comes into the picture. So in the coming lectures, we will know how that was done, how the self-attention works. Thank you. Hi. In this lecture, we will see what exactly happening inside the attention layer. So let's say this is our input matrix X. So let's say the sentence is he is bad. So we will convert this into a vector, right? And let's say the dimension of this whole vector is around 3 into 512. So let's say this is as input matrix X. So the next step is we have to calculate 3 matrices called as key query value matrices. So let's see how to generate those matrices. So we'll have three weight matrices called as WK, WQ, and WV, which are initialized randomly, and we will learn optimal values during training. So first, what we have to do is we have to multiply the input matrix X, which is initialized with some random values here as well, with WK, WQ, WV to get key query value matrices. So we have to multiply the input matrix X into WK a vector to get the key matrix. Now we will multiply the input matrix X with WQ, we'll get the Q matrix. We'll multiply X with the value matrix, WV matrix, we'll get value matrix. So once we get key query value matrices, so next step is to compute the dot product. So computing dot product between two vectors usually tell us how similar the vectors are. So by computing the dot product between the key and query matrices, we will know how similar a word in each sentence to other words in the sentence. So if you look at the following picture, so let's say he is bad. So this is the query matrix for the same he is bad. This is the key matrix. Now we have to do the dot product. So we will do q dot k transpose. Now we will get a matrix. Now if you look at the bottom matrix carefully, so this is it now 3 by 3 matrix. Now if you look at the values, so he to he, the value is 120, right? Because the similarity is more, because I think the both words are same, the similarity is more. When you look at he and is, the score is little bit less, and he to bad, the score is little bit less again. And again, if you look at is to is, the score is high, but is to he and is to bad, the score is 95 and 90. So what basically it tells is that when you do a dot product between two matrices here, that is key and query matrices, it helps us to know how similar a word in each sentence to other words in the sentence. So this is the first step. We have to do the dot product between key and query matrices that we generated in the previous step here. Now, once you have done the dot product between the key and query matrix, you have to divide it by the root of dimension of key matrix. So why do you want to do that? So because the dot product can produce very high magnitude values with very large vector dimensions, which will still result in very small gradients when passed to the softmax function in the next step. So the idea is to scale those values by dividing it by root dk. So that is the dimension of the key matrix. So we can say in the short, it's for stable gradients. And the next step is to normalize the values. So in by using softmax. So this is the thing, softmax of key dot query divided by root k. Now we will multiply with the value matrix with the above result. So once that is done, so we have to multiply with the value matrix after getting softmax of key dot query divided by root k. We will multiply that whole thing into value matrix. So why are we multiplying with the value matrix? Because we don't want a scalar score as output, rather we want vector of futures as output. So when we do key dot query dot product, right, we usually get the scalar values, but we don't want scalar values at last, right? We want the vector, a vector. So for example, if I type a query into a search engine and if it tells me that the score of the best matching web page is 0.94, well, that doesn't help me, right? I want the actual content of the web page. So that's why here in the same case, we just don't want the scalar values after we are doing a dot product between key and query. We want the vector values. So that's why we are also multiplying it with the value matrix. So you can see it in this diagram. So we are doing the dot product and we are dividing by root dk. So value is 8 because the, let's say the dimension of k is 64. Now the softmax of the result that we got in the previous step, we'll get this result. So you can see the values got reduced, and here by applying softmax, the values now are between 0 to 1. So now if you can look at the last line. So let's say if, in the previous case we have seen like how we can know how we can teach the model whether it refers to banana or monkey. We want it to refer to monkey, right? So once you get this scalar values, right? When you multiply with the value matrix, then this is how it will looks like. For it, this is how it looks like. So for 8 word, it will be the weightage is 0.0. But if you look at the monkey, the weightage is 1.0. For others, again, the value might be less, 0.0 or some other very less value. But if you look at the monkey case, monkey word, the value, the weight which it was representing is 1. So that is high. So this is how we can able to teach the model saying that for it refers to monkey but not banana. So and next are the multi-head attention. We will see it in the next lecture. Hi, in this lecture we will learn about multi-head attention. So in the previous lectures we just went through one attention, but the author proposed to have multi-head attention. So there are two reasons for this, because if you are using multiple attentions, you can able to learn different features. So let's say if this is the image, and if you apply multiple attention layers to this image, every attention layer will try to learn some feature out of the image. So one attention layer might learn about the image itself, about this particular lady. Another attention might learn something in the background like the sky. Another attention might learn about the clouds. Another attention might learn about the mountains. So having multiple attention will help to learn different features. So another reason is that since we do a lot of initializations for the weight matrices, sometimes there might be bad initializations. So what happens if you have bad initializations is that the model might learn something that it should not learn, and sometimes it may not learn anything. So in order to overcome that problem as well, the author proposed to have multiple attentions instead of just one. So this is how we calculate multi-head attention. So let's Z1 is what we calculated previously. So we apply softmax on the top of dot product between query and key matrix divided by root of dk into value matrix. So we do it for eight times. So Z up to Z8. So then we concatenate all Z1, Z2 up to Z8, and we will multiply with the weight matrices W0. So this is how multi-head attention is calculated. So in the next lecture, we'll go through about positional encoding. Thank you. Hi, welcome to this lecture. In this lecture, we'll go through what is positional encoding. So unlike in RNN, where we pass word by word, but in Transformer, we feed all the words in sentence parallelly, so that it helps in reducing training time and learning long-term dependencies, which are the drawbacks of RNN. But the problem is, how do you tell the model the words order in sentence? Because word order is very important. Let's say for language translation. So let's take an example here. So let's take this sentence. Even though he did not win the prize, he was satisfied. If I just change the not from starting to and replace it at the end, even though he did win the prize, he was not satisfied. The meaning of the whole sentence got changed, right? So the order of the words in a sentence matters. So if we just pass the input embedding matrix, transformer cannot understand the word order. So along with the input embedding, that is the input matrix X that we have seen in the previous lectures, we will add positional embedding as well. So this is how we add it. So let's say this is our input embedding, X equal to this is the matrix. Then we will add the position matrix, and if we do the sum, and we will get the resultant matrix. So the positional encodings have the same dimension as the model embedding, so that the two can be summed. So how to create this matrix first? So in order to create that matrix, these were the functions that were used. So author used sinusoidal versions of sine and cosine functions of different frequencies. So pause refers to position of the word in sentence, and D refers to embedding vector size. I refers to position of the embedding. So we will use sine function if I is even, and cos function if I is odd, based on the position of the embedding. So in the next lecture, we will recap the encoder block. Thank you. Hi, in this lecture, we'll just do a recap as per what we have learned so far. So this is the input embedding, and we will also this positional encoding. So we'll add these both embeddings, and we'll pass that to the first encoder layer. In the first encoder layer, what we have is a multi-head attention, and that output is passed to the feed-forward neural network. So this is all happening in one encoding layer, right? So now we will see what's inside feed-forward neural network. In feed forward layer and add and norm layer. So consists of two dense layers with ReLU activations. Add and norm component is basically a residual connection followed by layer normalization. So skip connections or residual connections are basically used to allow gradients to flow through a network directly without passing through nonlinear activation functions. So nonlinear activation functions by nature of being nonlinear cause the gradients to explode or vanish. And the layer normalizations are used to stabilize the network, which results in substantially reducing the training time necessary. All right. So that's why we use skip connections and add norm layers. And the next lecture, we'll go through decoder components. Thank you. Hi. In this lecture, we'll go through decoder section. So let's say this is the source sentence. He is good. Now, as you know, we convert into input embedding. We'll add positional encodings, and we'll pass it to the encoder layer, first encoder layer. So simplicity case, I'm just considering two encoders here. In original paper, there were 6 encoders, right? So let's say the output that was coming from the last encoder layer will be the representation of the source sentence. That representation is passed to the each decoder layer, and the decoder will decode the representation, and it will try to predict the target sentence. That is here, that is French. So ILEST bon. So let's see how it happens during the testing time, how decoder works during the testing time. Okay, during the step 1 process, so the decoder will see the tag called as SOS. So time equal to 1, step time equal to 1, the input to the decoder will be SOS, that is start of sentence. At time step t equal to 2, the decoder takes the newly generated word from the previous time step t minus 1 and tries to generate next word in the sentence. That is, the decoder takes SOS and IL, that is from the previous output, and will try to predict the next word, that is EST. Okay. At time step t equal to 3, it will be SOS, IL, and EST is the output that was generated in the last time step. So that will be added as an input, and it will try to predict BOL. At time step t equal to 4, it will be SOS, IL, EST, BON. Once the EOS that is end of sentence is generated, the decoder has completed generating this target sentence, and it will stop. Okay, it will stop at the point when it encoded EOS tag. Okay, this is how decoder works during the testing phase. So let's look. So this is just the overview again. So we'll have he is good, and we'll convert to input embedding. We'll add position encoding, send it to the encoder blocks. We'll get a representation from the last encoder block. We'll pass it to the each decoder block, and we will also have output embedding and a positional encoding in case of decoder, and we'll pass it to the decoder layers, and at last we get the target sentence. So these are the three main components in each decoder. So you will have something called as mask retention. We will see what it is, how is it different from encoder retention that we have seen in the encoder block. And we have something new layer called as encoder decoder retention and feed forward neural network. So decoder during training. So during testing, decoder predicts the target sentence word by word in each type step. But during training, as you already know what should be the transformed sentence, we will just add a start of sentence token to our target sentence and send as input to the decoder as shown below. So if you look at this diagram, so during the training time, since we know what should be the target sentence for he is good, so we will just add it as an input to the encoder, like with SOS start of sentence tag, and we'll convert to the embedding and we'll just add the positional encoding and we'll pass it to the decoder layers. This is during the training process. So in the next lecture, we will see what is masked multi-head attention. Okay, thank you. Hi. In this lecture, we will look at self-attention, that is masked attention. We call it as masked attention in the decoder layer. So we'll see how is it different from the encoder layer. So mostly it works same as an encoder with a small change. So again, we will create three new matrices called as query, key, and value. Since we'll have multi-head attention, so there will be h number of QKV matrices, and these matrices will be created by multiplying input x. That is the transformed sentence in this case, right? In decoder, it's a transformed sentence because we know what it is during the training process. So we convert that into embedding and we'll multiply that embedding with the weight matrices WK, WQ, and WV to generate Q, key and value matrices. So same as what you have seen in the encoder layer. But there is small change compared to encoder attention is that during testing time, decoder will see the words that were generated till the previous step, but not all at once, right? So in order to incorporate this during training, we need to mask all the words that are not yet predicted by the model. So let's take the example of this. So we will do the dot product between Q and K matrices divided by D root of dk, and let's say we got this matrix. So now at time step one, right? At time step one during testing phase, sorry, we'll only look at the tag SOS, but the model won't at that point it won't look at IL, EST, and BON, right? It will predict. It should actually predict IL. So in order to incorporate these changes in the training as well, so what we do is whatever when the model sees the SOS tag, at right side of the SOS, we will mask all the other tokens. So we mask it here all the other right to the SOS to negative infinity. So in the time step two, the model will have the data about SOS and IL, right? But it won't have data about other tokens like EST and BON. So you have to incorporate that change in the training as well. So in order to do that, whatever is right to IL will mask those tokens. So we masked EST and BON. So same in the third row up to EST. So we have SOS, IL, and EST, but we don't have a data about bond. So we have to mask it. So with minus infinity. At last, we have all the four. So once you apply softmax on top of it, those negative infinities values will be converted to zero. So this is the small change compared to encoder block. Since in the decoder during testing phase, it only has the information until the previous time step, and it should not look at the future. So to incorporate that change in the training process as well, we do the masked multi-head attention. So that's the only difference. Okay, thank you. In the next lecture, we will look at encoder decoder multi-head attention. Hi. In this lecture, we'll go through encoder decoder multi-head attention block. So this is the extra layer that we will encounter in the decoder section. In encoder, we don't have this block. So we will see why do we need this block. So for attention, we need key and value matrices, query key and value matrices, right? So we usually get them by multiplying input matrix with WK, WQ, and WV. Since now we are getting data from two different input sources, how to create those matrices. So if you look at this block carefully, you are getting two input sources. One is from output of the decoder mask attention, and another is from the source representation from the encoder. So previously in other attention blocks, what you have seen that we have only one input source, so we have no problem. But in this case, for encoder decoder attention, we are getting two different inputs. So how do you create those matrices, Q, K, and V matrices? So basically, query matrix is created from mask attention matrix, and key value matrices are created from encoder representation. So you basically create the query matrix with mask retention output into WQ. That is the output that you're getting here. And the key and value matrices are created from the encoder representation output into WQ. So you'll take the representation that was coming from the encoder block and you will multiply with the WK and WV to generate key and value matrices. But why? So the representation of the target sentence is obtained from query matrix since it's obtained from the mask retention. So we have the target sentence here, right, in the decoder block while you are embedding output embedding. So basically, so the representation of the target sentence is obtained from query matrix since obtained from the mask retention. And the key and value matrices hold source sentence representation as they were created from the encoder representation. So basically, when you do the dot product between the query and key matrix that was coming from output of mask retention and from encoder representation, basically it will tell us how similar words in source sentence to the target sentence. So the next steps are same as we commonly do in attention. I hope you got this point. So we do the dot product between the query and key matrices. Now basically it will tell us how similar words in source sentence to the target sentence, because the query is coming from the mask retention output and the key matrix is coming from the source representation from the encoder, right? So the next steps are same as we do in attention. So we finally get multi-head encoder decoder, and we concatenate Z1, Z2 up to ZH, and we'll multiply with the weight vector W0. So this is common. So that's about encoder decoder multi-head attention block. And that's it for this lecture. Thank you. Hi. We have seen the other two stages, right? Decoder mask retention and encoder decoder attention layers. Then we will look at the feed forward. So same as encoder, there is no change. You will have add add a norm layer and you will have the skip connections. There is not much change from the encoder. So once you get the output of the last decoder layer, right, that is passed to the linear and softmax layers. So usually the linear layer generates logits which whose size will be equal to the vocabulary size, and logits is sent to softmax layer to get the probabilities. So loss used is cross entropy loss to minimize difference between the predicted probability distribution and actual probability distribution. So let's say this is the decoder one. Let's say this decoder last layer. Then from that you will get the out. You will take that output, and you will so linear layer by taking that as an input will give us the logits. So which size will be equal to vocabulary. Say let's say we have vocabulary of 3 words: I, est, and born. So it basically give logits for those 3 words, and once you pass that to softmax layer, it will give you the probability distribution. So in this case, BON has the highest 0.7820. Let's say I predicted INEST, and the next word I usually predict is the BON because BON has the highest probability score of 0.78. So that's how the linear and softmax layers work. So this is the overall summary, the architecture. So we convert the source sentence to input embeddings. We'll add the positional encodings, and you will have self-attention layer, and then on top of it, add and norm layers, and you will have some feed forward layers, and you will have multiple encoder blocks like this up to 6, and then the output of the last encoder block, which is a representation of the source sentence, is passed to all the decoder layers, and each decoder layer, in each decoder layer, you will have self-attention, add and norm layer, and encoder decoder attention. And at last, the output that was coming from the last decoder layer is passed to the linear layer. And from linear layer, you will get the logits. And that logits were sent to the softmax. And the softmax layer will give you the probabilities. So based on the highest probability score of a particular word, you will predict that word as the next word. So that's all. This is the summary of the overview of the transformer architecture.